exciting hour of the day. We're very pleased to have Alex Peysakhovich from Facebook AI Research. Giving the first talk. Take it away.
All right. Hi, everybody. Yeah, so my name is Alex. I'm going to sort of hopefully give a lighter, less math-heavy talk to kind of wind down the day. So this actually is, rather than talk about kind of one paper in depth, I figured I would go and talk about something that I and a bunch of collaborators have been working on for actually quite a few years at this point. And it's sort of a common thread that runs through a bunch of papers. And it's about how ideas from machine learning can be used in game theory and the idea of using machine learning to build game abstractions. So this sort of comes from a kind of perspective of like game theory as engineering. Is kind of multiple ways to take that, but really I typically think of the engineering part of game theory as either doing something like agent design, right? So we have some strategic situation, we need to build maybe an AI agent that needs to go and enter it, and we want it to do well, whatever well happens to mean in this case. Or mechanism design where we know we're going to have some strategic agents and we're actually designing the game such that their interactions are going to give us some kind of outcome that we like. And these two things have in common that in practice, we're going to often face very complicated environments, and we're going to run into a lot of computational results that tell us that even in simple places, things that we might want to compute are very hard to compute. And so if we want to scale it, we often can't just like brute force it. So the idea that I'm going to be talking about today is, again, we didn't invent this. This has been around for a long time. And I really want to think about the work on poker AI as a place where this idea of game abstraction, kind of really took off. And the idea of an abstraction is, imagine that we have some game. So we want to build an agent that's going to be good at, let's say, 2-player no limit Texas Hold'em. So we this is a 2-player zero-sum game with imperfect information. So we know that what we'd really love to do is compute a Nash equilibrium and then just play that strategy when we go and play someone in Hold'em. And the problem with that is that even though we know how to compute these equilibria, when you have this many nodes in your game tree, you're going to wait until like the heat death of the universe before you're going to get your equilibrium strategy. So the idea of abstractions, at least in the poker literature, at least in the earlier poker literature, this is sort of changing or has changed, is we have kind of hand-tuned heuristics where we say, okay, well, we're going to take some of these nodes in our tree and we're going to put them together because they're really kind of the same node, or we're just going to ignore certain parts of the tree because we're never going to get there. And we use that to basically take our big game, make it into a simpler game, solve for the Nash in the simpler game, and then we're going to play the Nash strategy in our original game. This is kind of the poker way of doing abstractions. And I'm going to talk about a couple of things that we've been working on, which all sort of have the following pattern. We're going to take a complicated game. We know from game theory how to solve a kind of simpler version of that game. And then we're going to use some kind of machine learning technique as the little bridge between, well, how do you map this into this? And then ideally, this is sort of invertible in some way. And we're going to lift the solution up to the big game. So the first kind of example that I want to talk about, and this is what got us into this research, is thinking about playing social dilemmas. So, this is the prisoner's dilemma. This is like the most studied game theoretic concept, I think, of all time. Like biologists do this, psychologists do it, like everybody talks about this. And the reason that this is so popular is not because we really care about these like 2-action, 2x2 games, but it's because we think that repeated prisoner's dilemmas, in particular repeated prisoner's dilemmas, are kind of like natural abstractions of lots of situations that we face in reality. And so there's this whole line of research, which I'm going to sort of point back to this kind of like Axelrod tournament, where people are basically saying, okay, if we're going to be playing, I'm going to build a strategy for the repeated prisoner's dilemma so that when I match with a new partner, I do, quote, well, right? And well here, again, sort of depends on what the paper means, but I think in general, it's kind of like, I want to have high payoffs, kind of like no matter who I get matched with. This is kind of the zero-shot coordination or cooperation environment. So again, giant literature on all of this that sort of encompasses a general family of strategy that do these three things. So first of all, they say, well, a good strategy sort of cooperates when your partner cooperates. It defects when your partner defects, right? So it punishes. And then it allows that if you did defect on me, but then you start being nice to me later, we go back to cooperation. So the actual way you do this, right, if you think about, like, the simplest of these is tit for tat, which is like copy what the guy did before, but there's like a giant family of all of these that all kind of look like this. And so we've sort of converged on this is the way to play repeated two-player prisoner's dilemmas. Okay, so let's think about, let's scale up from the 2x2 game to this very simple grid world. Let's say I am blue, you are red, we can walk in all the cardinal directions. And randomly, coins will appear on this grid world. They're either my color or your color. If you pick up your coin, then, let's say you get a point. And if you pick up the other guy's coin, you get a point, but they lose some points, right? So obviously, like when I describe it, you're like, well, this is just like a bigger prisoner's dilemma because there's a strategy called cooperation, which is pick up your own color. And there's a strategy called defection, which is just go around and try to eat everything. But when you think about like an RL agent doesn't have these kind of, high level concepts of cooperation and defection. Their policy in RL is just a mapping from states, which is, what does the board currently look like? And maybe what is, a kind of history of play, to actions, which are walk up, walk left, walk right, walk down. So the basic idea here is going to be, and this is kind of our first two papers on the topic, is going to say, okay, well, let's use reinforcement learning or deep reinforcement learning, right? So for this, you can do kind of standard tabular things, but you can, as soon as you start getting bigger, you got to start using some function approximation, et cetera, to map our policy space so that now our policy space is going to look like cooperate and defect. So kind of the basic algorithm, in these, and then a couple of follow-up papers, is we're thinking about a world where we're separated into, yes.
Just a clarifying question.
Yes.
States, the key thing for reinforcement learning is what the algorithm reinforces. So what are your states here?
That's a great question. So the choice of state, typically we sort of think of it as like, well, when I give you the MDP, the state space is presented. But actually in, practical reinforcement learning, the choice of the algorithm that you're using to do the learning sort of also defines the state space, right? So if you have something that has memory, then the state is, board state plus some memory clicker, right? Whereas if you just have something that inputs the state and the state meaning the board position, then that's your state. So,
and in your case, what's the state?
Sorry?
In the results you're going to show us, what did you take the state space to?
So here in all of these papers, we look at the state as just what is visually available, right? So here the state is going to be where are the players on the board and where are the coins, if any, on the board.
Thanks.
So we're going to take, but that's a great question, and one which we talk a lot about in the papers. And I want to sweep under the rug for the talk, but of course you caught it, Drew. Anyway, so we're thinking about a world where we have two phases. We have a training phase where we have access to the game, and we can use that to construct whatever we're going to do. And later in the test phase, we can use the policy that we constructed in the training phase with a new partner. So in the training phase, we're going to do two things. We're going to construct a policy just using, here you can do this with a tabular RL algorithm, but you can also do it with a, your favorite multi-agent reinforcement learning algorithm. But you give it control of both agents, and then you construct the policy which optimizes the sum of the utilities. Now you pull that policy apart for an A and a B agent, and that's your C policy. Now you do the same thing. Imagine that at test time you're going to play as player 1. We're going to construct a policy for player 1, which is going to try to minimize player 2's utility. And we're going to allow player 2 to kind of maximize against that if we want. And that's going to be our D policy or our punishment policy or a minimax policy, if you want to think about it in like a folk theorem kind of sense. And then in the new partner phase, right, what we're basically going to do is we're going to do exactly what something like the folk theorem would tell us to do. So we're going to use the cooperative policy. We're going to somehow detect whether our partner is also using a cooperative policy or not, and then we're going to respond appropriately. So again, now we're sort of getting into like, well, what's the trick about how do you actually choose how do you actually detect whether your partner is using a C policy or not? You could see if they're matching the actions that you want them to match, but actually in practice, it's very fragile and doesn't really work. And so what we come down to in the two papers is that essentially there's two ways that seem robust. One is you use the Q function from your learned cooperative policy to sort of look forward, right? So you say, okay, well, my partner took action A, and that has affected my Q value by, whatever, some amount. Now, had they taken the action that I thought that they were going to take under the cooperative policy, what would have been my future value, right? So now I'm saying, how are you affecting my future value by your actions today? And when we sort of sum that up over time, and when that starts getting low, we start saying, okay, this guy is probably cheating. And sort of choosing, again, the threshold is going to depend on how much noise we think the other person has, et cetera, et cetera. You can do that, or you can look backwards at the realized payoffs, which is sort of a simpler but has other disadvantages, where what you basically say is, okay, well, we've been playing for 10 rounds. And I know that when we're both cooperating, I sort of expect a payoff of 20. Let's check my current payoff. Well, if my current payoff is sort of 20 plus or minus some amount, I say, okay, the person's probably cooperating. And if I look at my payoff and I say, oh, look, it's lower than I expected, this guy's probably cheating. So then we start defecting. So again, very similar to what you would expect from once you've written it down in this form, it's very easy to apply kind of folk theorem style intuitions to how you actually go ahead and swap between these policies. So this is sort of our prisoner's dilemma version of this, but we've actually thought about applying very similar kind of abstractions, and I don't want to go into too much detail kind of here at the sake of time, but similar ideas we've applied to coordination games. To stag hunt games, and then I think kind of importantly to these coordination games where it doesn't really matter what we do as long as we do the same thing, right? So in this paper we kind of study driving, right? It's really important that we both drive on the left or both on the right side of the road. Or here we think about a cooperative card game, Hanabi. So anyway, just kind of if you're interested, these ideas go far beyond the prisoner's dilemma. But the thing that I want to sort of also mention in this talk is, that was sort of agent design. Now let's talk about abstractions for market design. So let's think about a very simple environment. Fisher markets, we have a market, there are n buyers, there are m goods, each good has a limited supply, each buyer has some budget B. An equilibrium in this market is an allocation of goods to individuals and a price per goods such that the allocation that I give to each person maximizes their utility given the prices in the budget, and the total allocation is supply feasible, right? So basically you have a demand curve, you have a supply curve, you cross them. So we might care about computing equilibrium allocations in these markets for various reasons. One reason why is this is actually a mechanism with very nice properties. So there's this idea of competitive equilibrium from equal incomes, which is a mechanism when you have a bunch of items and you want to assign them fairly to individuals. So the way that CEI works is you say, okay, why don't you all report your valuations for each item to me? maybe a combination of items, kind of depending on the language that we're allowing. We give you a budget of fake money. We solve for the equal budget equilibrium of this market, and I hand you back the allocations that I've just computed. So this is really nice because it's going to inherit a lot of really nice properties from the market equilibrium. In particular, there's going to be no envy. When the market is large, it's going to be incentive compatible. And in the linear additive case, it's going to maximize national social welfare. So it's kind of like just a good mechanism. It's actually used in practice in university course allocations in a bunch of places. The problem with it is it's not very scalable in the general setting, because with general utilities, we have a lot of hardness results about computation of equilibrium. And even if you think about the very simplest case, which is additive valuations and divisible goods, meaning lotteries, yes, you can solve this with a convex program, but n to the 100 is polynomial time, and yeah, that's not a scalable solution. That's just polynomial time. And this kind of happens to be one of those problems. Yeah.
This is a very old.
Yeah, so variant is sort of the original. Yeah. So I mean, Buddhist is where all of this stuff starts getting actually used, right? All of the course allocations, like course potential.
But I don't understand for additive, they're strongly from.
It's not that fast if you have 1 million buyers and 1 million buyers. Again, like, so we can talk offline, but it's having actually tried to do this at scale, like, yes, you can solve it with either the convex program or there's a bunch of like primal dual approaches. Like if you make your market of like size 1 million by 1 million, like it doesn't, like, yes, if you have servers, it's going to work, but it's not going to scale to like even bigger things.
So remind me, when this is used in like business school,
yeah.
finance and so forth, what types of valuations?
So they have additive, but they also allow some amounts of complementarities. And they also don't do randomization, right? So they do kind of discrete demands. So you have to solve a MIP in order to do every demand computation. So that's what makes it actually quite slow. And the divisibility thing actually is not that big of a deal. Like in practice, all these things are like very integral. I mean, they also don't want multi-unit demand, right? So if there's like 10 seats in a class, they don't want you to get 5. So it's a little bit of a that problem has its own thorns, basically.
But they must have a lot of students, right? So are they taking like a week to solve this, or
So in one of the papers, in one of the earlier papers, they talk about basically they run it. At that point, they say, okay, we have a cluster, and we run it overnight on a cluster to get this. And I think they're doing per. Don't quote me, but I think they're doing per year, and then somehow combining it. But I'm not sure. Like, but basically, like, yeah, it sort of works at that level. But if you do like 100x that, there's no way that stuff is going to scale.
And I think it's probably approximate market.
Yes, it's approximate. Yeah.
So they have some room.
that's not for additive, right? That's for when you allocate courses. It's the utilities are arbitrary kind of.
They're not quite arbitrary because so remember, it depends on the language that you allow people to actually express, and I think they only allow you to express valuations, and then they have conflicts, right? So you say I can't get this course and this course because they're at the same time, and then I think also they do prerequisites somehow. So it's not like general utilities, and again, for general utilities, like you might not be able to find anything, right? Like doesn't even exist. So it's a class of utilities where you can get integral solutions, but it's not. Yeah. Anyway, So again, let's just think about the sort of divisible and additive case for a second. And so in this paper, we sort of say, okay, how do we do some abstraction to solve large versions of this? And so what we're basically doing is the following idea. So, in the additive divisible case, you can just write down a valuation matrix where the rows are buyers and the columns are items. One thing that we know how to do in machine learning is approximate matrices by lower rank versions of those matrices. Even if you have like missing values or things like that. And then the idea is that once you have an approximate left and right factorization of your valuation matrix, you can think of these as embedding vectors for your buyers and your items. Now, take your favorite clustering algorithm. In the paper we do k-means, but it doesn't really matter which one you do. And now cluster your embedding vectors. And what you're essentially doing is you're taking your buyers and your items and you're kind of like clumping them together. So like these two buyers become one buyer and these two buyers become one buyer and these two goods become one good and so on. And because of the way that you've factorized the valuation matrix, you can actually just take the centroids of your clusters and now sort of impute valuations for each representative buyer for each representative good. So now you've got this abstracted matrix, which can actually be like quite a bit smaller than your original matrix. You solve your equilibrium of your abstracted matrix, and then you just go ahead and you lift your abstracted equilibrium by just saying, okay, well, this representative buyer represents these 5 buyers and he's got these items. And so you can split them, kind of evenly, or you can do some kind of recursive splitting within each buyer. So this is gonna be a lossy abstraction. We do have I think a fairly obvious kind of theory result in the paper that the quality of your, in terms of like mechanism design quality measures, the quality of your solution compared to the actual optimum is going to be sort of linearly proportional to your factorization loss and your clustering loss. The thing that I think is a bit neater is, in the paper, we actually collect a bunch of data sets where people express willingness to pay for various items. And what you see if you just do like a bi-clustering on the matrix evaluations is that these things do have kind of low rank and clustered structure. So it means that, the more of this structure these things have, the lower this loss is going to be, and the better your approximate solution is going to be compared to what would be your real one. Anyway, so that's kind of, we then go ahead and have a bunch of different other, ways of, because this is basically a building block, right? Like anytime you're going to do a linear additive utility in an equilibrium, you can always do it in the abstraction. And so we sort of talk about this. If you want to do this in robust utility maximization, you can kind of do it online. It has a lot of connection to incorporating these sort of algorithmic fairness ideas, because a lot of the algorithmic fairness ideas can be expressed in terms of the buyer vectors that you end up getting. And then sort of, it's connected to things like Shapley value computation in cooperative game theory. Anyway, so TLDR, we got to do a lot of computation when we do engineering in game theory. In many cases, we know how to solve simple versions of games, but we can't really scale it. We can take machine learning, abstract big things, solve our simple solutions, lift the solution back up. Cooperation, coordination, market equilibrium computation. Again, not saying that we've nearly exhausted this idea. I think there's a lot more to go here. So yeah, thank you.
Thank you very much, Alex, for the very interesting, intriguing work. We have a lot of questions, I guess, already. And please, Dylan, let me know if there are anything.
Oh yeah, there's nothing in chat right now.
Okay.
Hi, I'm really curious to know about the Fisher market application. That's like a really highly decentralizable computation. I mean, whether if you want to do it, I don't know, with distributed comics optimization or just there's like algorithms to do that. Like, it seems like that should be something that you could handle millions of like buyers and goods if you do the right optimization. Like it's the simplest type of market. So going through the abstraction, you're losing guarantees. And I'm not sure actually if the computation becomes that much easier than if you actually decentralize everything.
I mean, so I'm not a convex optimization expert. My co-author on those papers does happen to be, so it's sort of a better question for him. But, you know, he seemed like the fact that he came and went and wrote a bunch of these.
But I think the same actually co-authors have a logarithmic time like computation guarantees for the linear efficient market.
Yeah.
So it's not really catching.
There are sort of like theory optimization guarantees, and then like you actually go ahead and actually run the optimization, and it like
is the issue that you don't actually have linear utilities in the applications you care about?
no, we think about linear utilities. I mean, you know, again, like it also doesn't have to be either or, right? Like the point of the abstraction is that what it's doing is it's reducing the size of your optimization problem by.
I understand that point, but I think what's more interesting is if you actually were able to abstract out a market that was harder, that we can't actually compute things for, like something like an error-to-burn market, onto a efficient market, and then you were able to compute it. But otherwise, you're taking a problem that's already easy to compute and reducing it to something that's even easier to compute while losing guarantees.
Yeah, I mean, I think, so I'm going to disagree that it's easy to compute in practice, but that's fine. You know, that being said, you know, the linearity is not. Okay, so well, what are other classes that you can do this kind of abstraction? So I think that a very similar abstraction technique can be applied to if you allow kind of pairwise complementarity sort of preferences, right? Where because you can write pairwise complementarity preferences as kind of a.
Is that Leontief, you mean?
No, not Leontief. So this is kind of like a long. Do you want to talk about this offline?
Yeah.
Okay, because
Now I have a question about the answer.
Okay.
No, go on.
Yeah, I think like it's an interesting question, and you know, there are trade-offs, right? I mean, there's the computation with the abstraction, the gain. I mean, it really depends on the application of the thing. So maybe let's take that offline.
Yeah.
But it's interesting. So.
Hi, yeah, really interesting, thanks. So with regards to the first part of the talk, I really like the idea of defining a cooperative policy as, you know, binding two agents together in a cooperative setting first and then taking that policy afterwards. But if I understand it correctly, you define cooperative policy as just maximizing the sum of the utilities in this case. And I guess this goes for like simple prisoner dilemmas.
Yeah.
But I would also see like maybe this is orthogonal to, so you're optimizing for efficiency. Maybe this is orthogonal to like equality. In some cases, for example, in some prisoner dilemmas, if you have the defective payoff be very, very high in comparison with the cooperative one. So how do you deal with that?
So that algorithm, right? You don't have to really. The cooperative policy can be anything, right? So you can say that the cooperative policy is the thing that, you know, maximizes Nash welfare, right? The product of the utilities, and you can train it in exactly the same way, and then you can apply the sort of folk theorem logic in exactly the same way, which is I watch what you do. If you're maximizing the Nash welfare, then I also do it, and otherwise I minimize your welfare. Right now you need sort of guarantees about that the min max is actually lower, right? Like I can sort of punish you enough to get you to do the things that I want, but it's a general thing about enforcing kind of whatever payoff you like.
Okay, so you can go for whatever metric you want or even combination. Right. Yeah.
Right.
Okay.
The important thing is that the thing you're trying to enforce is also a thing that the other person agrees is a good thing to enforce, because otherwise.
Yeah, that makes sense. Yeah. All right. Thanks.
Okay. Also, a question on the first part. These sort of high-level strategies. You have to hand engineer, so a prisoner's dilemma,
Yes.
defect cooperate for coordination, go on the same or not. Do you see any way of trying to automate that part as well, that you extract out the relevant high-level strategies?
Okay, so this is a place where I actually have a lot of disagreement with like a lot of other people in Marl. I think there's a bias in machine learning or AI or whatever you want to call it to sort of like do everything from the data. You know, like, oh, we don't want inductive biases. Like we want like, you know, we want it to come from nothing. But like, why? You know, like we wrote like, you know, we've written like hundreds and thousands of papers about the prisoner's dilemma, and we like understand how social dilemmas work, and we like, you know, we've sort of converged on an answer, and it seems like throwing, you know, like, why throw it away?
I mean, I'm thinking more like, could you then apply it to a game where you don't know yet what the high-level strategies are?
Yeah, so there's, I mean, there's versions of this. You know, Jacob Forster has a series of papers where what they do is essentially you do reinforcement learning, but you, within your, let's say, policy gradient, you include the other guy's policy gradient. So now you sort of like take actions to get that person to maximize your reward. So when you do that in like these prisoner's dilemma, like generalized prisoner, whatever you want to call them, games, you end up with things that look like tit for tat, because we know that's the answer. You know, it's unclear. Yeah, like, I guess we just sort of like need more context, right? Like, but you know, yes, if you don't know the answer, you can probably do other stuff. But if you know the answer, you should definitely hard code the answer, because you know the answer.
I guess, sorry, but as a follow-up to this, like, aren't you suggesting that sort of like you, in principle, you can implement some kind of like, you can use the effectively the folk theorem to, you know, kind of like, you know, force a social welfare maximizing thing, like in any game?
I mean, this is basically what we're doing, right? So like, because what does the folk theorem want? It says, what is the thing that you want? And then, you know, what is the thing that you're going to do if you don't do what I want? And so that's kind of what we're computing. The one trick with the RL part is, how do you detect, like, what does it mean for you to not do the thing that I want? Right, that's the thing that becomes, because in the, if you're just a normal form stage game, you're like, yeah, you didn't do B, so like, you know, we're done. But
I guess your suggestion is to look at the payoff that I was expecting to get. If I get worse payoff, then I'm gonna.
Well, right, but it depends which way, right? You can either look backwards at your realized payoffs, or you can look forwards at your expected payoffs, and there's kind of trade-offs to each one.
Right.
So,
but I guess in relation to that question, you can do that in any game, even if you don't know it a priori, right? Like, it definitely, like, two-player games is very clear what you wanna, what this might be fair.
Right.
So yeah.
Well, but again, like, you also want, the other person to actually go along, or the other player to actually go along with what you're doing, right? So like, I get 90% of the value, like, folk theorem enforceable, like, are you actually going to do it? I don't know.
Yes, it's kind of a follow-up question to what we've been discussing. So basically, what you have in mind, if I understood correctly, is a setting in which you have imperfect information. And so I was wondering, you know, in practice, you know, since basically you're motivated by practical issues, you also typically have incomplete information, which basically means that, as you were saying, what cooperation means depends, right, on what's my prior over the payoffs, which means that sometimes I might, you know, step into a relationship in which we're both cooperating, we just don't realize it, right? Because, you know, and so, which is kind of natural in complex games, which is a natural application. So it would be nice to see, you know, how this works actually in practice in settings with incomplete information.
So the algorithm that looks backwards at your realized payoffs, right, works in incomplete information. You know, but
then I guess the question
where you put the threshold, right?
There you go.
But you can only set the threshold kind of empirically, right? So you roll out, like, you have all these strategies, so you roll them out 1,000 times, and you say, okay, let's say the 5th percentile, the 10th, you know, right? Like you can follow a quantile, and the quantile is like, how much do I let you get away with possibly cheating at the expense of, by accident, you know, starting a nuclear war?
Yeah, but also what I have in mind is that if you train them, you know, using their own subjective knowledge on what the total payoff is, and now we disagree on, you know, what that total payoff is, we might end up with different strategies, which means, you know, that we, again, you know, my payoff sucks. Does not suck because you're not cooperating, you're cooperating in a different way, and I just not realize it.
Yeah. No, I mean, and this is always the problem, right? That like, you know, you also need these cooperative strategies to be like compatible in some way, right? So, I mean, it's just a harder problem. And I think there's no real, like, you know, if you think about some of the coordination stuff that we've done and other people have done, right? That is a lot of this question of, okay, well, there's multiple ways that we can achieve the high payoff together. How do we pick one? And I sort of view that as a separate problem from the like, well, is this person cheating or not? But like, I agree, you have to solve both to do a thing that works.
Very interesting discussion. We're running out of time, so let's thank Alex again and take everything else offline.